Hello! On May 12, 2026, Epic Games released Preview 1 of Unreal Engine 5.8. Along with many other features, it includes production-ready status for MegaLights. In this tutorial, I'm going to cover everything you need to know to use MegaLights effectively. How it works under the hood, how it behaves compared to the classic deferred rendering pipeline, which settings can matter and why, and how to work with it practically. Before we get started, we need to understand why MegaLights is a big deal. And for that, we need to understand what it replaces. The classic pipeline in Unreal Engine 5 uses deferred shading. Here's how this works in simple terms. For every light that's within range of the camera, the engine does two things. First, you compute a shadow map or ray trace shadow for that light, and second, you apply the light's contribution to every pixel it affects. Want to do that for 10 lights? No problem. You do it for 50? Bit extreme? Could maybe work. Want to do that for 200? Now you've blown your frame budget. Problem is counting lights per pixel. Imagine a pixel on the floor of a nightclub. It might be inside the attenuation range of 50 different LED fixtures, and the classic pipeline would evaluate all 50. But when you actually look at the energy contribution, 80% of the light could be coming from just a single fixture. So you just paid the cost of 49 evaluations to get 20% of the result you actually need. And that's not good. Virtual shadow maps, introduced in Unreal Engine 5, helped. Caching shadow map pages cuts down repeated work. But caching only works when lights and objects are static. The moment anything moves, like some dancing NPCs on your nightclub floor for example, and the cache invalidates. In the MegaLights demo you could see this, as hundreds of moving bots destroyed any caching scheme entirely. So what are the alternatives? We could do ray traced shadows per light, but that's still linear in complexity, still needs denoising, and it's still not scalable to hundreds of lights. There's also Reester, a high-end NVIDIA approach which achieves pretty excellent quality, but requires 23 times more ray traces than a single sample stochastic sampling method. A console that can only afford one ray per pixel cannot use Reester as a baseline. And that's where MegaLights comes in, which basically took the idea of Reester and made it more performant. The answer that MegaLights puts forward was to approach the problem completely differently. Don't evaluate all lights, don't trace per light, but instead trace a fixed number of rays per pixel, and then stochastically select the most likely important lights, and then let a denoiser reconstruct the final image. The result is that performance becomes constant, regardless of how many lights there are in the scene. Quality does depend on lighting complexity per pixel, but for a typical game scene, that trades pretty well. This last thing, however, is important. The perspective when using MegaLights is backwards. More lights does not cause less performance. It causes more noise. This can be a trap. Turn on MegaLights in your scene and poof, performance is magically fixed. But that doesn't mean that there will be no noise. You have to check that instead. So let's walk through the MegaLights pipeline stage by stage. Here are the 5 steps. Stage 1. Sampling. This is where MegaLights decides which lights to care about for each pixel and which ones not to care about. It runs at a downsampled resolution by default. By default it uses half resolution using a checkerboard pattern, but you can also make it run at full resolution. For each sample position, it reads the G buffer and picks a certain amount of light samples using a technique called weighted reservoir sampling. Now, what is that, I hear you ask? Well, not all lights are sampled equally. Each light gets a weight based on how much it's expected to contribute to that pixel, given the surface normal and material. Specifically, the BRDF luminance with logarithmic perceptual scaling. In other words, brighter lights with better angular alignment get more samples. And, crucially, MegaLights uses a mechanism called sample guiding to bias sampling towards lights that were visible last frame. Here's the mechanism behind this sample guiding, which is one of the most important innovations in the system. After each frame, MegaLights builds a per-tile list of lights that were actually visible, meaning that their ray traces were not blocked. These lists are then stored in an 8x8 pixel tile, and in the next frame, each pixel looks up its tile's visible light list and preferentially samples from it. 80% of your budget goes to last known visible lights. 20% is spent looking around to check if any new lights have appeared. This 20% is called the discovery budget. This discovery budget ensures that MegaLights reacts to scene changes. When a door opens and a previously occluded light suddenly becomes visible, those discovery rays can catch it. When history reprojection fails, for example during fast camera movement or sudden disocclusion, the discovery budget temporarily gets pushed up to 50% to refine the lighting environment quickly. For area lights specifically, MegaLights adds one more refinement. There is a 2x2 bit mask per light in the visible list. This bit mask marks which quadrant of the light surface was visible. So during sampling, random samples are biased away from blocked quadrants. So if a large rect light is half inside a wall, MegaLights learns not to send rays towards the obstructed half. This reduces the amount of wasted traces on area lights. Then it's time for stage 2. We trace. For each selected light sample, MegaLights traces a ray to test visibility. This is where the actual shadow information comes from. So this tracing happens in layers. First, you have the screen space traces. They are short, conservative rays traced against the depth buffer. These run on every pixel, always, regardless of other settings. They catch fine detail that's absent from the simplified ray tracing scene, things like contact shadows under a chair leg or a thin wire casting a shadow on a wall. They also serve a second purpose. They offset the ray origin from subsequent hardware ray traces, preventing self-shadowing artifacts caused by mismatches between the rasterized geometry and the simplified bounding volume hierarchy representation. If you're confused about what a bounding volume hierarchy is, it's basically the scene that the ray tracer uses. And then the second thing it does is it uses hardware ray tracing against the near-field BVH. This is the primary shadow computation. So rays are traced against simplified nanite fallback meshes with roughly 150 meters of the camera. This is inline ray tracing, which runs efficiently on console hardware that supports it. And the BVH is built once for all the lights simultaneously. This is a huge advantage over the old model where each light needed its own shadow map. Optionally, you can extend the coverage further. There's far-field ray tracing against heavily simplified merged H-Lot1 geometry for distant objects. This does require world partition HLODs to be built. For alpha mask geometry, like foliage, a retrace using any hit shaders is available. It is accurate, but it is expensive, so avoid alpha masking in content where possible. And individual lights can opt into virtual shadow map sampling instead of ray tracing, which gives fully precise shadows from full nanite geometry, but then you're back to the old system, which has the cost of per light memory and the GPU overhead. Then it's time for stage 3. We shade. Once visibility is known, MegaLights evaluates the light contribution for all the visible samples. It uses pre-integrated irradiance together with IES profiles, light functions, and sample widths. The shading cost is fixed per pixel, and it only depends on the tile type, not how many lights there are. Which brings us to stage 4. We update the visible light list. So after shading, the visible samples are gathered in an 8x8 tile and are written into the guiding list for the next frame. This step is pretty cheap. Takes around 0.05 milliseconds on a PlayStation 5. And it's what makes the sample guiding system work across frames. Then it's time for stage 5, denoising. All the light contribution from all lights have been accumulated into 2 render targets, the diffuse and the specular. A single denoiser then reconstructs the final high-quality image from this stochastic input. This denoiser has 2 parts. It has a temporal filter and a spatial filter. The temporal filter reprojects the previous frame's result and accumulates lighting over time. If new data is far outside of the neighborhood bounds, the history is then discarded quickly so that fresh data can fill in the space. The spatial filter then cleans up any remaining noisy spots using a sort of specialized rotation brush that aligns the noise to edges. This is called a sparse rotated kernel, if you were wondering. This rotation is per pixel, and TSR, the temporal super resolution, Unreal's latest anti-aliasing solution, then smooths out the remaining holes. There's one last thing that is used to improve the quality, and that is shading confidence. If the visible light list accounts for a large fraction of the total expected energy at a pixel, MegaLights flags that pixel as low noise, and it just skips the entire denoiser and passes it straight to TSR. This helps preserve specular sharpness, which is especially important on character faces, which can be sensitive to blurring. So what about the performance cost? Well, the sources tell us that on a PlayStation 5 running at 1080p, With 941 area lights on the screen, all casting shadows, the entire MegaLights pipeline costs 5.51 milliseconds. That is sampling, tracing, shading, the visibility list, the denoising, all combined. And that replaces all of the old deferred lighting pipeline. Shadow depths, light shading passes, volumetric fog shadowing, the whole lot. So let me quickly summarize how MegaLights compares to the other options you have in Unreal Engine 5. Traditional shadow maps with deferred shading scales with the number of lights, but you get constant quality per pixel. This works great with scenes under 30 to 40 shadow casting lights, but starts to break down past that. Also, area shadows for area lights need to be approximated. You also have the per light ray trace shadows, which still scale with light count, so you're just replacing shadow maps with ray traces. But you still need one denoiser pass per light. This gives you better quality than shadow maps for area lights, but the scaling problem does not go away, which brings in MegaLights. MegaLights has a constant GPU cost, but the quality degrades instead of the performance. MegaLights supports over 1,000 shadow casting dynamic area lights on current gen consoles without tanking your performance. And on top of all that, it enables physically correct soft area shadows that contact harden naturally near the shadow caster. The breakpoint where MegaLights wins over the classic pipeline is roughly when your scene starts to exceed 50 shadow casting local lights. Beyond that, the overhead of the stochastic pipeline may actually not pay off. Above that, MegaLights tends to be strictly better. So, use MegaLights for the right kind of scene, and also take into account that not all platforms support ray tracing. While MegaLights can do software ray tracing against the distance fields of the scene, hardware ray tracing is strongly recommended for quality and performance. So let's have a look at the actual settings. Let's start by enabling MegaLights as the default for a project. Now, remember, this is just changing a default. You can also enable or disable MegaLights in specific areas through the post-process volume. You can find this under Edit, Project Settings, Rendering, and then Direct Lighting. Something just fell. You'll see the MegaLights toggle there. Enable it. And when you do, the editor will prompt you to also enable hardware ray tracing. Do that as well. Now remember, MegaLights has a software fallback, and it's not necessary to have hardware ray tracing, but it is strongly recommended if you want the right quality. Let's move to the details panel. In any light actor, you can find two MegaLight-specific properties, which is Allow MegaLights, which is a boolean that lets you exclude individual lights from the system if you would need so, and the MegaLight shadow method, with two options. Ray tracing is the default. It adds 0 per light cost, but there's also virtual shadow maps, and you should use that sparingly. It tends to add a significant per light CPU, memory, and GPU cost to generate shadow depth maps. Preserve it for lights where the ray tracing scene's simplified geometry causes visible shadow artifacts, and precise, hard-edged shadows from nanite are pretty critical. Also, you can enable or disable MegaLights per zone using post-process volumes. This is pretty useful if you want to run MegaLights in larger environments, but you want to fall back to traditional lighting in a smaller interior room, which maybe has 3 lights. Now let's take a look at some console variables. So the first one, MegaLights.Allowed, gives you a global toggle, which can be useful to override scalability levels. With the numbers of samples per pixel command, you can control the ray budget per pixel. The default is 1 sample per pixel, but you can crank this up all the way to 16 if you need so. This is useful for cinematic shots or for your movie render queue output to pre-render cutscenes, for example. There is also a downsample mode command, which you can set to 0 for full resolution, or you can turn down the resolution if you need more budget. For volumetric fog and lit translucency, you can change the GridPixelSize and GridSizeZ using these commands. Higher values mean sharper volumetric shadows at a higher cost. If you need a directional light inside MegaLights, for example, soft moonlight that also needs volumetric fog, for example, you can enable it through Directional Lights 1. Big warning, be careful with this. Strong directional light tends to just dominate the sample selection, and this will completely starve your local light discovery, especially indoors. So keep it for dim, soft directional light sources only, like the moon, for example. If you're gonna put a blasting sun into your scene, just use the virtual shadow maps instead. As a side note, for Niagara particle lights, you can set the simple light mode to 2. This makes MegaLights handle all particle lights globally. Or you can leave it at the default and opt in per emitter via the light renderer module properties. Okay, great. Time to profile some performance. There's different things you can use for this. A good console command would be to turn off your async compute with async compute 0. Otherwise, the async compute will overlap dispatches and that can distort the raw timings. If all your local lights are on the ray tracing shadow method, turning local light primitive interactions to 0 will remove the entire legacy per light CPU tracking cost, which can save you some overhead. Alright, let's talk practically. Let's put MegaLights into our scene and let's look at it as an environment artist. Which habits and workflows does it still require? Number 1, and super important, please do not think that MegaLights gives you free rein to add unlimited lights into your scene. You still need to take into account the attenuation radius. And it's actually one of the single most important habits to keep MegaLights performing well. If you have tons of overlap, you will get tons of noise. MegaLights must allocate some sample budget to every light whose attenuation sphere overlaps a pixel. So a light with a massive attenuation range that's essentially too dim to contribute at most distances will still steal sample slots from more important nearby lights. Try to trim those as much as you can. Another really important one is, do not put lights inside of geometry. If a rectangular light is halfway inside a wall, the engine still needs to trace rays towards the entire surface of that light, including the half inside the wall. Those rays immediately hit the wall and contribute nothing, but they use up your sample budget. Yes, the area light is still split into quadrants, but the engine still needs to take that into account. It's better to just avoid the problem altogether. You can use this console command to visualize which rays are going in which direction. If rays are going into walls, the light placement might need some adjusting. Combine this console command with the shader print lock console command to freeze the visualization. You can then fly around the scene to understand the ray geometry from different angles. This is invaluable for diagnosing shadow artifacts. Another very important tip is to just use IES profiles where you can, or light functions instead of light fixtures. Light functions are evaluated cheaply during the sampling pass and can create complex emission patterns if you need them. You should just use a light function to shape your light wherever possible, as this can prevent quite a bit of noise. Also keep into account the nanite fallback mesh quality for your shadow casters. When you see gaps or missing shadows on important geometry, the first suspect should be the nanite fallback mesh being too low poly. Just open the static mesh editor, go to Settings, set fallback target to relative error, reduce the fallback relative error value, and click Apply Changes. Then rebuild the mesh. You can check the Ray Tracing Debug View mode to see the actual simplified geometry that MegaLights is shadowing against. Use this sparingly though, a complex BVH can mess up your performance. When it comes to the directional light, make sure that you plan your approach. For most projects, you should just keep this console command for directional lights at 0. Let the sun be handled by the standard pipeline with virtual shadow maps. MegaLights is designed for local area lights. That's its strength. The directional light integration is better suited for soft moonlight versus sharp sun shadows across an open landscape. Also be aware of your per pixel lighting complexity. Use the light complexity heat map to find which pixels have a lot of light overlap. When you see blurry or ghosting direct lighting in a specific area, that's usually the symptom. The fix is almost always one of the following: reduce the attenuation radius of the nearby lights, narrow any spot angles, use barn doors on rect lights, or merge several small lights into a larger light and get the same effect with an IES profile or a light function. Yes, MegaLights allows for many lights, but remember, you have to take care of your overlaps. MegaLights also supports textured rect lights and complex layered materials. These add some tile classification overhead, but they work correctly. Just be aware that a textured rect light are the most expensive light type in the sampling pass. And finally, one mindset shift that the original SIGGRAPH paper also highlights: artists given MegaLights tend to just go wild. This system is intentionally forgiving by design. It degrades rather gracefully instead of just crashing your frame rate. But that doesn't mean it's a magic bullet. Light sources still reduce the sampling performance or increase noise. The disciplines of tight bounce, clean placement, and using light functions or IES profiles over having actual geometry still apply. The ceiling is just much higher than before. Current version of MegaLights also comes with a bunch of limitations. First of all, the forward renderer is not compatible. It's only for deferred rendering. So if your project uses forward rendering, MegaLights is not an option. Also, directional light cloud shadows are not supported. Subsurface scattering thickness estimation, also not supported. Water, clouds, and heterogeneous volumes, and local volumetrics are also not yet integrated. These are areas of active development, however. Also keep into account that mobile, the Switch, PlayStation 4, and Xbox One are not supported. MegaLights targets hardware ray tracing capability on PC and on current-gen consoles. The movie render queue also doesn't have dedicated MegaLights support yet. For high-quality renders, use TSR as your anti-aliasing method or send the temporal sample count to around 8. Both approaches resolve the stochastic lighting pretty decently in an offline context. One of the known quality issues that Epic is actively working on is that the denoiser accumulates in render resolution while TSR accumulates in display resolution. This means that specular highlights on character faces can lose sharpness or develop ghosting. It's not a blocker, but it's something to watch out for on close-up character shots. So let me bring this back to where we started. MegaLights in Unreal Engine 5 solves a problem that was previously unsolvable at console frame rates, rendering hundreds of dynamic shadow casting physically correct area lights in a single unified pass. It does this through stochastic light sampling with visibility-guided sample selection, hardware ray tracing, and a purpose-designed denoiser. The key things to take away is that performance is constant, regardless of light count. The quality depends on the per-pixel lighting complexity. The ceiling on how many lights you can use in a scene has now moved from a couple of 50 if you're careful to basically unlimited with some pretty graceful quality degradation. So these changes make a lot of new things possible, but use it correctly. Hope you found this interesting. Thanks for watching.